Okay, this is video 6A, Thermodynamics, Part 1. Now, in this chapter, we're going to be talking about the nature of energy. Energy is an aspect of matter that makes things happen or has the potential to make things happen. And when energy is transferred from one object to another, it appears as work or as heat or both. Heat is thermal energy, and the symbol for it is Q. And work is a force acting over a distance. Work equals force times distance. Change of energy is equal to the heat involved in the process plus the work done to or by the process. The sign of energy transfer is defined by this system's perspective. What we're really talking about is an energy exchange, where energy can be heat or energy can be work. Heat can flow from the system to the surroundings, or from the surroundings to the system. Likewise, work can flow from the system to the surroundings, or from the surroundings to the system. Now, the first law of thermodynamics is the law of conservation of energy. And what it says is that energy can neither be created nor destroyed. However, it can be transferred from one object to another, and it can assume different forms. The material or process whose energy changes we study, that's defined as the system. And everything else is what we define as the surroundings. The law of conservation of energy requires that the total energy change in the system and the surroundings must be zero. Delta means change. The change of energy of the universe equals zero, which equals the change in energy of the system plus the change in energy of the surroundings. One is gaining or losing energy, and the other is losing or gaining that exact same amount of energy. And the Greek letter delta means change, and it's always calculated the same way, the final amount minus the initial amount. Now, since matter can be converted to energy in nuclear chemistry, and vice versa, with Einstein's equation E equals mc squared, it's probably more correct to say that the total mass and energy change in the universe is equal to the total mass and energy of the system plus the total energy and mass of the surroundings. But this is sophomoric because unless you're dealing with nuclear changes where vast amounts of energy are involved, the change in mass is so minute as to be completely negligible. So we just talk about the law of conservation of energy. Now, that means if we compare the amount of energy in the system and the surroundings during a transfer, let's say we have these energy gauges, and this is the system energy gauge, and this is the surroundings energy gauge. And you can see the system energy gauge is half full or half empty, depending on if you're an optimist or a pessimist. And the surroundings is 1/4 full. And then there's a change, and we see that the system has lost 1/4 of its energy, but that the surroundings have gained that amount of energy. You see that? So that same amount of energy that was lost by the system has been gained by the surroundings. Now let's talk about the signs of the change of energy. Here we have a system with an initial state up here. It's of higher energy than the final state. And since we always calculate the change in energy, the delta E, as the final state minus the initial state, that is going to give us the change. If we start here and it loses energy, and the final state has an energy here, what is the sign of delta E? So what we see is that this amount of energy is lost to the surroundings as the energy of the system falls from this higher state to this lower state. And that means that the final energy state is a smaller number than the initial state. So you're taking a smaller number and subtracting from that a larger number. So what is the sign of delta E going to be? Well, it's going to be less than 0. It's going to be negative for this exothermic process where energy is lost to the surroundings. Final state minus initial state is a negative number. We call that, by the way, an exothermic process. Now, what about the converse? If the system gains energy, then the initial state is of lower energy than the final state. The initial state is a smaller number than the final state. And as energy flows in, and we calculate the delta, then because it's always final minus initial, final state is a larger number, initial state is a smaller number, final minus initial must be positive number. And therefore, the delta E is greater than 0, a positive number. So you see how it works. If energy is lost, the sign of energy is minus. If energy is gained by a system, the sign of delta E is positive. Okay, let's take a look at this chemical system versus the surroundings now, our energy gauges, if you will. The system is 3/4 full. The surroundings is 1/4 full. So, which of these, A, B, or C, I'm going to ask you this in class, which of these, A, B, or C, is valid if the top starting point undergoes a change in which delta E of the system, the change in energy of the system, is negative? That's the question we're going to ask. Pressure volume work is work that is a result of volume change against an external pressure. So when gases expand, delta V is positive, but the system is doing work on the surroundings, so the work done is negative. So as long as the external pressure is kept constant, work equals the external pressure times the change in volume. The enthalpy of a system is the sum of its internal energy and the product of its pressure and volume. So the change in enthalpy equals the change in energy plus this pressure volume work. And this is a key point. For most of the processes, we'll consider P delta V equals 0 or is minimal. So delta E equals the enthalpy change, delta H, and that equals the heat at constant pressure. So enthalpy, the way we'll be using it in class, relates to the heat of a system being lost or gained at constant pressure. So in these systems, we want you to identify in which is delta H positive and in which is delta H negative. We'll be asking you this in class. You might study it so you can make an intelligent choice when we get to it. In System 1, the system is losing energy. System 2, system is gaining energy. Now, energy changes are what we call state functions. Like a change in altitude, they're only dependent on the initial and final points, not the path taken. So when you're going up a mountain, the change in elevation of the mountain is 10,000 feet. You look at the top point, you look at the bottom point, you subtract to get the total delta. But the path that you take, whether it's a curved, windy path or whether it is straight up the mountain is not a consideration when you're looking at elevation. And both delta H and delta E are state functions, and we are only concerned about the values of their final state and their initial state. Now let's classify energy. Potential energy is energy that is stored in an object, or energy associated with the composition or position of the object. Kinetic energy is energy of motion. Thermal energy is kinetic energy. So here's an example of potential energy. The ball's being held up. It has the potential for losing energy when you let go of it. And as soon as you let go of the ball, it begins to fall, and that potential energy has been transformed into kinetic energy. So it's an example in two forms of energy being transferred one into the other. The first law of thermodynamics says energy must be conserved, but it can be converted into many different forms. Heat energy, light energy, electrical energy, sound energy, nuclear energy, chemical energy, mechanical energy are all forms of energy. So here's a question I'll ask in class. Which form of energy is not involved when this flying pumpkin, I think that's what it is, lands on a car? Which form of energy is not going to be involved? Sound, electrical, heat, mechanical energy. So what we have here is a ball on a cliff, if you will, right here. The ball is being prevented from falling by a little rock. In order to get the ball to fall, we have to push it kind of over this little rock. And it begins to fall. That's ball number 2. And it lands up in the ocean in ball number 3. I should say lands down in the ocean. So we want to describe ball number 1, this one right here, sitting on the ledge, in terms of its relative kinetic energy and its relative potential energy. Does it have a high kinetic energy? Does it have some kinetic energy, or low kinetic energy sitting up here on the ledge? And the same for its potential energy. Does it have high potential energy, some potential energy, or low potential energy? Then we want to do the same kind of analysis on ball number 2, describing its potential energy and its kinetic energy. And ball number 3, the one in the ocean. For ball number 1, it has very low kinetic energy, but it has a high potential energy relative to the ocean down below. Now the falling ball, right here, number 2, that has obviously some kinetic energy, and it has some potential energy still, because it hasn't gotten to the bottom yet of the cliff. And finally, when it gets down to the ocean bottom, it would have a low kinetic energy and a low potential energy. Now what we want to do here is draw a potential energy diagram that shows the relative potential energy as a function of the event progress. When the ball starts out, where are we on this? Do we have low potential energy or high potential energy? This is ball number 1. And if you're saying, well, that would be high potential energy, then you want to start out right there. And it seems that would be a position of high potential energy. Now, if you notice, we have to push it over this little bump here to get it to fall. So as the event progresses, what happens to our potential when it rises up that lip of the rock? It goes up, doesn't it? As we push the ball over this little hump to get it to start falling. And then what happens? It begins to fall, and as it falls, it loses its potential energy. And finally it gets to the very bottom and has very little potential energy left. So we get a potential energy diagram that looks like this. We'll be drawing a number of these throughout the semester. So we want to learn how to do this. What about potential energy between a positive ion and a negative ion? These are electrical charges. We know that plus attracts minus. What's going to happen when these ions come together? So does it start out as a high potential energy, or does it start out as a low potential energy? How does it start out? Well, when the balls were far apart, that would be a position of high potential energy, over here somewhere. And as they begin to come closer to one another, we see that the potential energy falls until there is no potential energy in the system. Now let's talk about the units of energy. The amount of kinetic energy an object has is directly proportional to its mass and its velocity squared. 1/2 mv squared is the formula where m is mass and v is the velocity of the object squared. So when the mass is in kilograms and speed is in meters per second, what is the unit for kinetic energy? Well, that's a joule, defined as 1 kilogram of mass times velocity in units of meters per second squared. Now, you'll learn in physics classes that the joule is also defined as a force over a certain distance, but we're not going to use that definition here. Another unit of energy is called the calorie. A calorie is the amount of energy needed to raise the temperature of 1 gram of water by 1 degree Celsius. A kilocalorie, of course, would be 1,000 calories, and that's the energy needed to raise 1,000 grams of water by 1 degree Celsius. When you're sitting at the breakfast table eating your cereal and you're bored and reading the back of the box, you see the calories for the cereal expressed as a capital C calorie. And that's used in the food industry, and it means kilocalories, 1,000 small c calories. So the energy conversion factors, summarizing, 1 small c calorie is equal to 4.184 joules. And by the way, that's an exact conversion. It is not 4 significant figures. It's an exact number conversion. 1 large c calorie is the same as 1,000 small c calories, and that's 4,184 joules. And a unit of energy for electrical appliances is the kilowatt hour, and that's 3.6 million joules. Now, it might be instructive to do a little energy comparison. The energy required to light a 100-watt light bulb for an hour takes about 3.6 times 10 to the 5 joules, 0.1 kilowatt hours. Now let's compare that to a person running a mile. That's in the same ballpark, 4.2 times 10 to the 5 joules, or 0.12 kilowatt hours. Well, how about the energy usage per capita in the United States in one day? That's 9 times 10 to the 8 joules, almost a billion joules per person per day. In kilowatt hours, 250. What's really interesting is when you compare the U.S. consumption to other countries in the world. Afghanistan is 2.9 compared to our 250. Australia is 179. Brazil's 44. China's 66. France is 129. Haiti is 7.3. Now here, Iceland, tiny little Iceland, is more than double our usage, 541. But you have to understand, Iceland gets to use a lot of thermal energy or geothermal energy. And I'm pretty sure that's why it has such a sky-high energy usage per capita, because basically it's free in Iceland. Japan, 125. And of course, oil-rich Kuwait is 391. So that's a bit larger than energy consumption in the US. Mexico is 50.3. There are several types of enthalpy changes that chemists talk about. There's the heat of a reaction, which is the heat given off or taken on by a reaction. There's the heat of formation of a compound from its elements. That's what the heat of formation is. There's the heat of fusion. If you think of fusion as melting, that would be the heat involved when a solid melts into a liquid. And there's the heat of vaporization, of course, when a liquid boils and vaporizes, the heat of vaporization. Now, one thing we have to talk about that's confusing to students is the difference between temperature and heat content. This match over here has a very high temperature, but it doesn't have a lot of heat energy to it. If, for example, you wanted to boil this water, would you use this match, which is very high temperature, but not much heat energy? Or would you use a hot plate, which is nowhere near as hot as the match, but has, over time, much more heat content to it, and it would boil the water? So temperature is not the same thing as heat content. The quantity of heat energy absorbed is called the heat capacity. So that's when an object absorbs heat energy, its temperature increases. And the increase in temperature is directly proportional to the amount of heat energy absorbed. Some substances need only absorb a little bit of heat energy to see a big change in its temperature. Other substances can absorb a lot of energy, heat energy, before its temperature actually rises. So we call that proportionality constant the heat capacity. And the units of heat capacity are joules per degree C or joules per K. But really, in any one of these changes, we're talking about the change in temperature. So something has to absorb energy before we see a change in its temperature. It doesn't matter in these problems whether we use delta degrees C or delta K. They're going to be the same value, because we're talking about a change. Suppose we have a temperature of 25 degrees C going to a temperature of 30 degrees C. Okay? So that is a change of 5 degrees, isn't it? Delta 5 degrees C. Let's do the same kind of change with Kelvin. 25 is 25 degrees C. And let's say we're bringing that up to 30 degrees, which is 5 more, which is 303 Kelvin. And if you subtract 303 and 298, you end up with what? You end up with 5 Kelvin. So it's exactly the same value. The delta is exactly the same value, whether you're talking about Kelvin or degrees C. So we say that Q equals C, which is the heat capacity, times the change in temperature. And the heat capacity of an object depends on its mass. This is an extrinsic property, the heat capacity. It depends on its mass. A related conversion factor is the specific heat, which links the energy absorbed or released to a change in temperature and the mass. So this is an intrinsic property. The specific heat capacity is the amount of heat energy required to raise the temperature of 1 gram of a substance by 1 degree Celsius. Units are in joules per gram degree C, and actually we're talking about a change in temperature. So it really doesn't matter whether you're using degrees C or Kelvin, because the change in temperature will be the same in each case. And so this is an intrinsic property. Here are some heat capacities of common substances. Here's lead at 0.128, gold at 0.128, silver 0.233, copper 0.385, iron 0.49. And what kind of boggles the mind when you compare these specific heat capacities to that of water? Water is 4.18. Water has an extremely high specific heat capacity. It can absorb a lot of energy before its temperature actually changes. The molar heat capacity is the amount of heat energy required to raise the temperature of 1 mole of a substance by 1 degree Celsius. That too is an intrinsic property. So now we have a problem. Solid silver has a specific heat of 0.235 joules per gram degree C. How many joules are required to change the temperature of 25 grams of silver by 57.6 degrees C? So note that this is really the change in temperature. This is really a delta in temperature change, and we would set it up to solve for joules. The target of this question is joules. So our specific heat capacity of silver, 0.235 joules per gram delta degree C, multiply it by the mass and multiply it by the change in temperature, we will get 338 joules. Here's another one. A 200 gram sample of a metal at 50 degrees Celsius is added to 150 grams of water at 15 degrees. The temperature of water rises to 18.3 degrees Celsius. Calculate the specific heat capacity of the metal. So this time our target unit is the conversion factor of specific heat, and so that's what we want to end up with. And the useful units of specific heat capacity is joules over gram delta degree C. So grams and delta degree C are given, or at least the delta degree C can be calculated. We need to calculate the joules so that we can make up this specific heat capacity ratio. We have grams, we have delta degree C. After a little subtraction, we need to figure out the joules. Well, here's the deal. The law of conservation of energy says that the heat lost by the metal equals the heat gained by the water. In other words, energy is conserved. So the information telling us about the heat rise in the water is also going to be able to be used in order to calculate the heat lost by the metal, because it's going to be the same amount of heat energy. So here's how we would do it. We would use the heat capacity of water, 4.184 joules per gram delta degree C. We'd multiply it by 150 grams of water. That's the amount of water we have. And we multiply that by the change in temperature, 18.3 minus 15.0. And from that, doing that calculation, we would get 2,071 joules. So now we have all the information we need to solve this and get the specific heat capacity. 2,071 joules divided by 200 grams of the metal times the heat change of the metal, which would be 50 degrees Celsius minus the final temperature of both metal and water, 18.3 degrees Celsius. So that will give us a specific heat capacity of this metal of 0.327 joules per gram delta degree C.